traffic in this image. Across all of these vehicles on the road today, roughly 95% share the exact same structural opening mechanism, the conventional car door, hinged squarely at the front-facing vertical edge. This diagram outlines the physics keeping that standard in place. At highway speeds, heavy wind resistance presses firmly against the outward swing path of the door. If a latch fails during transit, the oncoming air acts as a fail-safe barrier, forcing the cabin shut. But before automobiles reached speeds where wind resistance became a survival factor, entry was dictated by an entirely different set of priorities. In the era of the horse-drawn carriage, passengers prioritized grace over aerodynamics. In this historical photograph, you see the origin of the coach door. Hinged at the rear trailing edge, the door swings entirely backward. This specific geometry allowed passengers to slide naturally outward from wide bench seating without navigating around a metal obstacle. These rear hinge systems, later dubbed suicide doors, perfectly answered the environmental needs of the time: passenger comfort and slow, aristocratic travel. However, as vehicle performance escalated, those early entry solutions met a physical threshold they could not cross. By the mid-20th century, automotive geometry evolved drastically. To maximize speed and aerodynamic efficiency, designers widened the vehicle tracks and dropped the chassis remarkably close to the asphalt. When you attach a conventional door to a chassis that sits inches off the ground, a standard outward swing physically scrapes against high sidewalks. Furthermore, the extreme width of these new sports cars trapped occupants inside when attempting to open long doors in restricted parking spaces. This immediate spatial bottleneck stripped the conventional hinge of its utility in the high-performance sector. Automotive engineers were forced to abandon standard horizontal logic, turning the car door into an open canvas for mechanical experimentation. The first response to low ground clearance was an exercise in subtlety. Without drastically altering the visual silhouette of the car, engineers at manufacturers like Aston Martin developed the swan door. This animated pivot point displays exactly how it works. The mechanism operates similarly to a conventional door, but the front hinge is anchored at a subtle, upward-sloping angle. When pushed outward, the door rises slightly, allowing low-slung panels to clear standard curbs. While the swan door conquered the low clearance problem, it still required significant lateral space to open horizontally. To solve the issue of extreme vehicle width, engineers had to look up. This rad Lamborghini Countach demonstrates the ultimate answer to horizontal width constraints. The scissor door abandons the horizontal axis entirely. By utilizing a single fixed hinge point near the base of the A-pillar, the door rotates vertically upward, requiring virtually zero lateral space. To improve passenger egress even further, high-performance manufacturers like McLaren took the scissor concept and mounted the hinges along the entire front pillar. This created the butterfly door, a dual-axis mechanism that causes the panel to rotate outward and upward simultaneously, widening the exit path for the driver. Pointing their mechanics toward the sky, engineers successfully navigated the physical realities of wide chassis designs. But in doing so, they permanently embedded highly complex, exotic hinge geometries into the manufacturing process. The DeLorean DMC-12, shown here, illustrates a highly theatrical response to structural constraints. Because the chassis required high side sills for rigidity, engineers hinged the doors directly at the central roofline. They opened straight up and outward, resembling a seagull in flight. The complete opposite of that theatricality is the purely utilitarian sliding door. By mounting horizontal tracks directly along the body panels, the door slides straight backward. This parallel movement solved tight lot clearance for commercial vans and minivans, maximizing entry for multiple passengers without swinging into adjacent traffic. Yet neither vertical wings nor sliding tracks could solve the absolute most extreme spatial constraint in modern driving, the ultra-compact microcar. Look closely at this BMW Isetta. With zero side space available for a traditional entry point, designers attached the entire nose cone to a single side hinge. The driver pulls the car's face open like a refrigerator, allowing direct frontal entry into the tiny cabin. Conversely, from this top-down perspective of the 1989 BMW Z1, you see a mechanism that discards swinging altogether. The drop-down door operates on a vertical drop, retracting directly into the lower rocker panels beneath the floor, allowing legal open-air driving with doors completely lowered.
Between 1950 and 1990, automotive engineering proved there was no single correct way to enter a cabin. The mechanics were dictated by the immediate physical realities of the surrounding environment. When environmental constraints are replaced entirely by a pursuit of extreme aesthetics, traditional side doors are completely phased out. Notice how the structural capsule in this concept moves as one piece. In the canopy mechanism, the roof, windshield, and side windows lift directly upward. Modeled entirely after fighter jet cockpits, it isolates the driver in a highly aerodynamic, singular pod. Despite the visual impact, canopy doors remain largely restricted to concept vehicles. The inherent danger of trapping occupants inside the glass capsule during a rollover crash prevents them from becoming a daily production standard. To find the ultimate mechanism, one that successfully marries the drama of aerospace engineering with the rigid safety requirements of street driving, we have to look at the modern hypercar. This white Koenigsegg demonstrates an entirely proprietary system, the dihedral synchro helix door. Built exclusively by the Swedish manufacturer, it solves every clearance issue simultaneously. This schematic isolates the first stage. The hinge pushes the door outward, sweeping exactly 90 degrees to clear the bodywork. Then it rotates forward around a synchronized axis. This geometry fully clears low sidewalks while staying below low garage ceilings. The synchro helix system resolves the spatial trade-offs of exotic performance design, allowing a hypercar to navigate tight urban environments while maintaining its dramatic mechanical signature. From standard front hinges to synchronized dual-axis helixes, the industry has engineered exactly 11 distinct ways to open a car. And functionally, a door does not need to be highly complex to protect the cabin. Manufacturers invest millions in exotic hinge engineering to make a definitive aesthetic statement, setting their machines apart through physical theater. The mechanism acts as the defining handshake of the vehicle. Engaging a scissor, gull wing, or swan door is a theatrical, mechanical prelude to the power of the driving experience itself. Over a century of design, engineers took the repetitive, strictly utilitarian action of sitting down and turned it into a testament to human obsession.